Hey guys, we missed you in class today. Hope testing went well. Said that I would provide a quick video of just a couple of problems from the lessons that we went over. We only did 3 lessons in class today. So I'm just going to hit the high points. And first of all, I want to go over example 1, which is in lesson 49. Now we've seen this type of problem before, but we're going to build on this in the next example. So I just want to refresh your memory here. But we're told by the problem, this is on page 331, we're told that if we have, if 6 books weigh 15 pounds, so 6 books weigh 15 pounds, and they want to know how much would 20 books weigh? So 20 books weigh what? Question mark. All right. And so what we've done in the past is we've created a little grid here, a little table, and we say we have kind of 2 different situations, and we've got a couple of rows here. The first row is our books, and so we've got books, and here is the weight. And so we enter in those values. In the first scenario, we've got 6 books and they weigh 15 pounds. In the second scenario, we have 20 books, but we don't know what they weigh. So that's the value that we're trying to find. So remember, the way that we do this kind of problem is we basically set up a couple of ratios that are equal to one another. So 6 over 15 equals 20 over x. And now once we have that equation, we can simply cross multiply, meaning we're going to multiply the 6 and the x together, and then we're going to multiply the 15 and the 20 together. And so 6x equals 15 times 20. And so that means if we divide both sides by 6, that x is going to be equal to 15 over 20 divided by 6. Now, we can simplify this a little bit and recognize that 3 will divide both into 15, give us a 5, and 3 will divide into 6, which will give us a 2. And then this 2 will divide into the 20, which gives us a 10. So that simplifies things a little bit, and we see that x is equal to 50. So 50 pounds is what 20 books would weigh. All right, like I said, that should be review. We've already done that. That's a L, by the way, and not a 1. But now this, really what they introduced into this problem was this particular lesson is, what do you do when you have rate problems? And what do we mean by that? You maybe remember from last year, I don't think we've gone over that this year yet, but the equation for rate, I do want to just review that very quickly here. And I'll tell you the way that I always remember the equation for rate. That is, I think about how fast you drive in your car. We say we drive, for example, 55 miles per hour. So it's always miles over hour. That's what the rate of my car is. Now, what kind of measurement is miles? Well, that's a distance measurement, right? And what kind of measurement is hour? What kind of a unit is that? That's a time unit. And so that means that it's basically our rate. Rate is equal to distance over time. Okay. So example number 3 in the book. And my computer's doing something weird. I don't know if you're seeing all that. Hopefully that's not too distracting. But we're told in this example that Julio is riding in a 50-kilometer bike race. So the full race is a distance of 50 kilometers. And he passed the 15-kilometer mark in 27 minutes. So he went 15 kilometers in 27 minutes. And the question is, if Julio continues to ride at the same rate, now realize this is our rate, 15 kilometers over 27 minutes is one rate. If he continues to ride at the same rate, what will be his time for the whole race? Well, if the rate is the same, then we can say 15 kilometers over 27 minutes is equal to whatever the distance is of the entire race divided by the time that it took him to ride the entire race. So we're told that the distance is 50 kilometers for the entire race. And so what we're trying to find out is, how long did it take him to ride that far. So now we have an equation just like we had before where we can cross multiply, and we can simply say that 15x is equal to 27 times 50. Just like we did before, we'll divide both sides by 15, and that gives us that 27. We'll use this dot notation here. 27 times 50 divided by 15. We can see that both the 15 and the 50 are divisible by 5, and so that gives us 10 and 3 here, and then the 3 will go into 27 9 times, and so we're left on top with 9 times 10, or 90 minutes. So 90 minutes would be the total time that it took him to ride in the race. Now, example 4 is connected with this, and example 4 says, what is Julio's rate in kilometers per minute? And so as it turns out, we can either use this side of the equation, or now that we know what x is equal to, we can use this side of the equation. So either would work. Actually, this right side is going to be simpler as far as figuring out the rate. So remember, rate equals distance over time, and the distance for the entire race is 50 kilometers divided by the time we found out to be 90 minutes, right? And so both of those are divisible by 10. That becomes a 9. That becomes a 5. And so the final rate is going to be 5 over 9 kilometers per minute. All right. So that's how we do these rate problems when we've got a ratio where there's a constant rate. We can set up a ratio like this and solve it like we've done with some of our other ratio problems. All right, so let's move on to lesson 50. So I'm going to erase this 49 here. I'm going to change that to 50. And this particular lesson is about solving multi-step equations. I know you've seen this before, so this should be familiar from last year. And we've certainly done some smaller versions of these types of problems, but we'll just have an extra step or two in order to complete the answer. Sorry, I'm having to erase this little by little. I feel like there's probably an erase all option on here, but I can't find that. So let's look at the first problem, which simply says 3x plus 1.20 equals 5.40. And we're asked to solve for x. So again, this is a multi-step problem. So what are the multiple steps that we need to take in order to solve for x? Well, first, what we want to do is subtract 1.2 from both sides. Now, some people learn to do that like this. So they'll say minus 1.2 there, minus 1.2 here. And they'll draw a little line, and they'll say, well, these cancel out. So we're just left with 3x equals 5.4 minus 1.2 is going to be 4.2. And then they divide both sides by the 3. That would be our next step. And that leaves us with these 3's cancel out here, and that leaves us with x being equal to 1.4. Now, another way to think about this, and again, I'm not sure how you learned it, so I'm just going to show you another way to think about it, is rather than doing a separate line here where we subtract out the 1.2, we can just think about moving the 1.2 over to this side. And whenever you move something that's added or subtracted from a number on the other side, when you move it to the other side, you just need to change the sign. So in this case, we would say that 3x is equal to, draw that x a little cleaner, 3x is equal to 5.4 minus 1.2. And then that gives us 3x equals 4.2, just like we had before. We divide both sides by 3, and we're again left with x equals 1.4. So whichever one you're most familiar with, you're most comfortable with, that's totally fine with me. As long as you come out with the right answer, it's just really a matter of how you've learned it before, and whatever helps you make sure that you don't make a mistake and you get the correct answer. All right, so let's do another one, another multi-step problem. And this time we'll do example 2. And example 2, let's see. We'll move on to example 3. This is a little bit tougher, so let's do that one. 3x plus 4 minus x equals 28. All right, so this one, we have an additional step that we didn't have in the last one that we need to do first before we do the same steps that we did in the last example. The first step in this one is we notice that we have two terms here on the left side of the equation with an x in it, right? So the first thing we want to do is combine like terms. So 3x minus x is going to leave us with 2x. So on this side of the equation, we have 2x plus 4 equals 28. Now we're left with the same steps that we had before. We're going to subtract the 4 from both sides, or move the 4 over to the other side and make it negative. It's another way to think about that. So 2x equals 28 minus 4. So that means 2x equals 24. Sorry, I was trying to make that 4 a little cleaner. There we go. And we divide both sides by 2. Our 2's cancel out, and x equals 12. All right. So you can always check your answer by taking whatever you get here in the end and plugging it back into the original equation. So that's a great way to just verify that you got it right. Let's try that real quick. We're going to plug in the 12 for x, right? Everywhere we see an x, we're going to plug in 12. And let's see if we get a true statement once we simplify. 3 times 12 is 36, plus 4 minus 12 equals 28. And then 36 plus 4 is 40, minus 12 equals 28. And sure enough, 40 minus 12, that's 28. And so 28 equals 28. So we get a true statement. That means that our solution is correct. All right, let's move on to the final chapter that we want to consider today. And some of the students hadn't seen this before, so this may be new to you. And it's the idea of negative exponents. What do you do with negative exponents? Let me change this stuff. 51, less than 51. And if you see, well, let's look at this example that we should be familiar with already. In fact, I went over this in class today because some of you made mistakes on this when it was on the test. So what is x to the 5th over x to the 3rd? How do you solve that? Well, what you do is you say you subtract the exponent on the bottom from the exponent on the top. And so you say x minus x to the 5 minus 3, or x squared. That would be our answer for that. All right, well, what if this was reversed? What if we had x cubed over x to the 5th power? Well, you do exactly the same thing. You do x 3 to the 3 minus 5, and that gives us x to the negative 2. So it's possible to have an exponent that's negative. And so how do we think about that? Well, there's a formula in the book that says x to the negative n is equal to 1 over x to the n. So if we wanted to write this answer here with positive exponents, we would change x to the negative 2. We would change that to 1 over x squared. We would just move the, if you've got a value like this with a negative exponent that's in the numerator, we would move that to the denominator and remove the negative sign. Conversely, if we had 1 over x to the negative 2, we would move, and since it's in the denominator now, we would move it to the numerator to make it positive, and we would say that equals x squared. Okay, so just think, that's to me the easiest way to think about it. When you've got a negative exponent, just move it to the other side of the fraction and it becomes a positive exponent. So with that in mind, let's see if we can do a couple of quick examples and we'll be done, and you guys can go about your business. Let's see. So this is example 1, and example 1 says, which of the following does not equal 10 to the negative 3? And so the first example they give us is 1 over 10 cubed. Well, that definitely equals this, because we said we can think of this as 10 to the negative 3 over 1. And how do we get rid of the negative exponent? We move it down to, it's in the numerator, we move it to the denominator. And when we do that, it becomes positive exponent. So 10 to the negative 3 definitely equals 1 over 10 to the negative 3, right? The next possibility is 1 over 1,000. And so if we think about it, 1 over 10 to the third power, what is that? Well, that is actually, if we raise 10 to the third power, that's exactly what we get. It's 1 over 1,000. So 10 to the negative 3 is also equal to 1 over 1,000. That's also true. The next one that they give us is 0.001. All right. Well, let's think about that. What have we learned when we divide by 1 followed by some number of zeros? If you divide any number by 1 followed by a certain number of zeros, you basically take the decimal in the number that's in the numerator and you move it to the left the same number of zeros as you have in the number that's in the denominator. And so if we think about the number on top here as 1.0, just so we can keep track of where the decimal is, and we divided that by 1,000, the answer would be equal to 1.0 with the decimal place moved 3 places, because we have 3 zeros, 3 places to the left. Okay, so that means we're going to pad this with some zeros just so we'll have enough room. So we had 1.0, we're going to move it 3 places to the left. 1, 2, 3. So our new answer is 0.001, right? We can just ignore this since it's a 0 to the right, at the end, to the right of the decimal place. Well, what is this? This is exactly the same as that, right? So turns out that this answer here is also the same as 10 to the negative 3. The last possibility they give us is negative 1,000. And there's no way that we can say 10 to the negative 3 would be equal to negative 1,000. So this is the one, out of all the 3 they give us, that's the one that is incorrect. Let's do just a couple more. I'm just gonna, instead of erasing everything, I'm gonna write this over here. If we look, it asks us to find the missing exponent. And so they give us 10 to the negative 2 times 10 to the negative 4. And they say that equals 10 to what? We put a box up here and say what exponent goes right there. Well, remember, when you're multiplying 2 numbers together that are raised to a power and the base for each of the terms are the same, so in this case, the base is 10 for both of these terms, then what you do is you add the exponents together. So this times this is equal to 10 to the negative 2 plus negative 4 power, or 10 to the negative 6. So that's what would go up here in our box, negative 6. And what if we had 10 to the negative 2 over 10 to the negative 4? Well, in that case, rather than adding the exponents together, we would subtract the exponents or take the difference between the exponents. So that would be negative 2 minus a negative 4, which is 10 to the negative 2 plus 4, which is 10 squared. So that would be that answer. And then finally, let's do one that's a little more complicated. Make some space for that. This is example 5 in the book, and we had 2 times x to the negative 1 times y times x squared times y to the negative 2 times z. They didn't like that when I put the little line through the z there in class, but it makes a lot of sense when you compare the z to the 2. My z's and my 2's look kind of similar. So that kind of looks like a z there, doesn't it? But you don't have to wonder if that's a z because I didn't put a line through it. So that's definitely a 2. But since that is kind of an ugly 2, you know what? I'll do you a favor and I'll try to make it look a little bit nicer there. It looks about the same, doesn't it? Anyway, so let's see how we combine these together. And what we want to do, what it's asked us to do, is express all of the exponents as positive exponents. All right. So we're going to start by combining together what goes together, and we can only combine the terms that are that have the same base. So, like, since both of these terms here, they're technically not terms because they're not added together. But both of these have x's for the base, and both of these have y's for the base. So those are the two sets of variables that we can combine together, and it becomes 2 times x to the -1 plus 2. Remember, when you're multiplying them together with the same base, both of these have x for the base, then you add the exponents together, and for y, you'd have y1 minus 2, since there's an understood 1 right here on this y. And then finally, we're left with the z kind of hanging out here by itself. All right. When we do the math for the exponents here, we get 2 to the first power for x, 2 times x to the first power. And then for y, we have y to the -1, and then all of that is multiplied times z. Well, like we said, we want to get rid of our negative exponents. We want everything expressed in positive exponents. So what do? We take this y to the -1 and we move it to the bottom of the fraction. Always, we can think of this as an understood fraction by putting it over 1, right? And so if we move that y to the bottom, what we get is 2 to the x. Now, when you have just a power of 1, you don't write that, right? So we're going to drop the 1 that's on the x there, times the z, and then we're going to take this y and we're going to drop it down to the denominator. So this is what our final answer would be for that problem. All right. Well, that was it. That's kind of an overview of what we went over today. Like I said, missed you guys in class. I know you weren't there for the whole thing, so feel free to reach out if you have any questions, and I will see you guys, Lord willing, in sometime next week.